So far, many types of air defense missile systems have been presented, which were used by the Soviet Homeland Air Defense, the PVO. Now it is time to talk about the air defense equipment of the Army Air Defense. Let's start with a maybe less known SAM system, the 2K11 KRUG family, or using its NATO code and name, the SA-4 Ganef. The KRUG was the first self-propelled mobile SAM system of the Soviet Army. However, before the appearance of the KRUG, the Army did not lack such equipment, but it was not so suitable for the need of the Army. Before the appearance and spread of the KRUG, Army-level air defense was provided by the S-75M Volkhov missile batteries for the first-line units. However, the Volkhov was a towed and not a self-propelled system. Its deployment and dismantling took approximately 2 hours. Additionally, it had numerous other disadvantages to be a practical army air defense system. Thanks to this, it was only considered a temporary stopgap solution. It was not particularly suitable for protecting mobile combat units. Essentially, the Volkhov was used for this purpose only out of necessity. The KRUG replaced the S-75M Volkhov in Army-level air defense from the mid-60s. The requirements for Army air defense differed from the SAMs of the PVO. The KRUG system had to be self-propelled to meet the needs mobile combat warfare. Additionally, the targets were completely different in nature compared to medium, heavy or intercontinental bombers. Tactical fighters and the newly emerging fighter bombers, as well as the subsonic strike aircraft like the A-6 Intruder, represented a completely different category in terms of maneuverability. The maneuverability of the missile had to be designed accordingly, besides many other things. There was no shortage of expectations, the list was quite long and the bar was high. Significantly larger engagement zone was expected compared with the SA-75 Win had. The maximum range had to be 45 km at high altitudes. The expected minimum target altitude was 3 km and the maximum was 25 km. The requirement for maximum target speed was 600 meters per second at high altitude, which was almost twice the speed of sound at 10 km of altitude. The fire control radar had to be capable of tracking a fighter of a size of a MiG-15 from a distance of 115 km. The expected deployment and readiness time was 5, yes, only 5 minutes. Designers had to think in terms of minutes, not hours, as were typical for the SAMs of the PVO. These serious requirements had to be met with the technical level of the late 50s. On February 13, 1958, the Central Committee and the Council of Ministers issued the resolution to start the development. The prototype acceptance test date was set for the third quarter of 1961. The new system was named KRUG, meaning circle, which also meant starting a new naming tradition. While the Homeland Air Defense missile systems were named after rivers, following the Berkut, Army Air Defense missile systems were named after geometric shapes. There was only one exception to this, but more on that later. The development was quite problematic. Many of its main components were developed in parallel from scratch. As a result, the development suffered significant delays. The low-rate initial production started only in October of 1964. The extra content deals with the difficulties of development and some technical curiosities, among many other things. In some areas, the system exceeded the specified parameters, while in the others it fell short, but the overall result was considered acceptable. The KRUG system was revolutionary in many areas and remained a completely unique system in numerous technical solutions among the Soviet or any other SAMs. The KRUG system, a KRUG brigade, consisted not only of radars, missile launchers and missiles, but as usual we focus on these, as well as the missile transport and reloading vehicles. A KRUG brigade consisted of 3 missile battalions, each with 3 missile batteries. This could be referred to as a full KRUG complex. Therefore, a brigade had a total 9 air defense missile batteries. Additionally, the brigade also had a technical battalion. In addition to these missile batteries, there were missile transport sections. The main assets of a brigade were as follows. One P-40 radar system for each brigade, which consisted one RL-128 long-range target acquisition radar and one PRV-16 Hatefinder radar. Each missile battalion had a 1S-12 SOC target acquisition radar. Its NATO name was Long Track. The 1S-12 should not be mistaken with the P-40 complex. Regardless the similar appearance of the 1S-12 Long Track and the 1R-128 are very similar, they are on a totally different organization levels. Each missile battery had a 1S-32 SNR missile guidance station, or more commonly referred Fire Control Radar Complex. Its NATO name was PAT-HAND. So, in a total KRUG brigade had 4 Long Track and 9 PAT-HAND complexes. Each missile battery had 3 2P-24 SPU self-propelled missile transporter and launchers. Each carried 2 missiles. One missile battery could have maximum 6 missiles ready to be launched. One battalion had 18, the brigade 54 of them. The SPU launchers were supported on battalion level by a missile transporter and reloading platoon. This had 6 TZM missile transporter and reloader vehicle and 3 TM missile transporter. This could carry a single missile per vehicle. All the main elements of the system were mounted on self-propelled track chassis to provide the necessary mobility on the field, except the towed Hatefinder radar and the missile transport and reloader vehicles. This ensures that the KRUG complex can keep pace with the combat units during relocation outside paved roads. The combat elements of the system had full nuclear, chemical and biological protection. A missile battery was able to reach launch readiness from March within 5 minutes. It has to be noted that only the missile batteries could be deployed within this short time, but for example, the towed Hatefinder radars could not do that. The video represents the 2K11 M1 variant. The significant upgrades compared to the earlier versions are mentioned briefly. One KRUG brigade replaced one Volkov regiment, which had 4 missile batteries. Using this comparison, it's easy to understand how much of an improvement was the KRUG. Now, we know the size of a KRUG brigade, which has 9 missile guidance stations in total, so it had 9 target channels. It could engage 9 targets at the same time nominally. How many units were defended by a KRUG brigade on and how wide of a front line? A KRUG brigade was assigned to every army group or front using the Soviet terminology, and another KRUG brigade to a single army. 2 or 3 armies consisted of an army group. A single army was built up from 5 divisions. The combat width of an army group was 200-250 km, an army half of this. The structure and organization of the Soviet Army and Army Air Defense will be presented maybe another time in a much more detailed form. Among the radars listed in the organizational structure, let's start with the P-40 radar system, which most sources and people confuse with the S-112 target acquisition radar. The P-40 designation actually refers to a complex, even though many people inaccurately simply call it P-14 radar. The P-40 system consists of 2 main equipment. The one RL-128 target acquisition radar, which measures the target's position in azimuth and its distance. The other component is the 1RL-90, or mostly known as PRV-9B, or the 1RL-132, better known as the PRV-16 Hatefinder radar. The electric power to the Hatefinder radar is supplied by the generator of the target acquisition radar. The PRV-9B was still mounted on a tow trailer, and its deployment took 45 minutes. The PRV-16 was self-propelled, but it is still needed 50 minutes to be deployed. The combination of the 2 types of radars provided the capabilities of a quasi-3-dimensional radar at the time, but with the limitation that only one target's altitude could be measured at a time, not all of them. For the KRUG system, the PRV-16 was not a crucial, because, as usual, if the target's azimuth was known, the fire control radar could find the target with a quick vertical scan. However, the P-40 complex was used not only by KRUG brigades, but also by radio technical units for target acquisition and guiding fighters, where knowing the target's altitude accurately was important during the ground-controlled interception process. It doesn't matter that the rotating antenna of the P-40's 1RL-128 radar looks very similar to the 1S-12, they were at different organizational levels and they were not the same hardware-wise either. Practically almost all sources confuse them or are saying that the two are almost identical, even though they are two different systems despite their almost identical appearance at first glance. The 1S-12 was used only by the KRUG system, and therefore only by the Warsaw Pact member countries, as will be discussed later. In contrast, the P-14 complex was exported more widely, also outside of the Warsaw Pact. The image on left shows the 1S-12 radar and its antenna details, which distinguish it from the P-14 complex on the right. The diamond-shaped antenna grid is missing from the 1RL-128 radar. For the 3 missile batteries of a battalion, the primary target acquisition radar was the 1S-12 SOC, but in case of need, manual target search was also possible with the S-232 SNR missile guidance station, but with very serious limitations. The self-propelled decimeter wavelength radar could detect fighter-sized targets from about 180 km at an altitude of 12 km. However, at an altitude of 500 meters, the detection range decreased to 55 km. The SOC was capable of searching for low-altitude targets, and like the P-80 radar of the S-75M Volkov, this radar also had the SDC device to reduce the effect of ground clutter. The radar emitted coherent pulses necessary for this. The explanation of the SDC mode is in the video about the S-75M Volkov system. New feature of the target acquisition radar was that it had limited altitude measurement capability, what the P-12 and the P-18 radar of the Dvina and Volkov system did not have. Its large parabolic antenna created 4 different elevation beam zones per rotation. Depending on the operating mode, it transmitted in each zone in a consecutive rotations or only in a selected zone. If the SOC swept the entire elevation range, it swept only one zone per rotation, but sequentially. In the first rotation, it covered between 0 and 4 degrees, in the second between 4 and 8 degrees, in the third between 8 and 14 degrees, and finally between 14 and 28 degrees. The system performed the switching electronically. It was not possible to measure the exact altitude of the target, but it was able to determine in which of the 4 zones the target was. Knowing the distance, a lower upper estimate of the target flight's altitude could be roughly estimated. The antenna rotation speed was 12 or 18 revolutions per minute. So, with a full forescan zone, even at the higher rotation speed, the radar picture in the given altitude zone was updated only in every 13 seconds. This was slower compared to the P-12 or P-18 radars, but for exchange, it provided more information to the crew. Since the system was mobile and quick deployment and readiness were specified, the data link between the target acquisition radar and the guidance station, as well as between the latter and the missile launchers, was designed accordingly. The 1S62 telecode channel provided radio telecode data transmission between the SOC radar and the 1S32 SNR guidance stations up to a maximum distance of 5 km. The 1S63 telecode channel connected the SNR and the missile launchers up to a maximum distance of 200 meters. If enough time was available, the radio telecode channel could be replaced with the P274 field telephone wire, improving emission control of the missile battery. But in this case, the deployment time was higher than 5 minutes. The KRUG was the first Soviet air defense missile system with monopulse target tracking antenna with an analog computer. At a time when digital computers were room-sized devices, it was a significant achievement to manage to install the necessary computing capacity and all required equipment on a single and mobile vehicle. The core of the system was the fire control radar and the guidance method. The KRUG was developed in the late 50s. Therefore, realistically, the choice was between only radio command and the semi-active guidance methods. Originally, a combination of the two was also considered. Ultimately, the designers opted for the pure radio command guidance due to its simplicity, and it has been proven because the S-25 Berkut and the S-75 Dvina used it. For small targets such as the F-104 and F-5 fighters, the detection range of the SNR was about 70-80 km at high altitude. The maximum indicated target was 110 km. Target tracking beyond this distance was not feasible, no matter how large the radar cross-section of the target was. The SNR antenna tower could be turned between ± 340 degrees relative to vehicle's longitudinal axis, but it could not rotate continuously like a target acquisition radar antenna. The SNR guidance station had the following antennas: AVS-1 monopulse target tracking antenna or RPC antenna, SPK radio command guidance antenna to guide the missile, AVS-2 wide beam missile tracking antenna receive only, AVS-2 narrow beam missile tracking antenna receive only, telecode antenna of the 1S62 and 1S63 systems. And besides the antennas, there is the TOV camera for optical target tracking, alternative tracking device instead the AVS-1 antenna. The KRUG system had a radical innovation over compared to the Dvina and Volkov systems. It was designed with an independent target and missile tracking antenna system. These were the AVS-1 and AVS-2. The target and missile tracking antennas could move independently from each other, whereas in the S-75 and Volkov system, both the missile and the track target had to be within the tracking range of the wide beam antennas. Thanks to this, the KRUG could guide the missile against the target with larger lead angle than the Dvina, Volkov or Neva systems. The target was tracked by the large yellow marked AVS antenna labeled with 1. Guidance commands were transmitted to the missile using the green-colored SPK antenna. The missile's response signals by the radio beacon was first received by orange-colored the AVS-2 wide beam antenna labeled with 3, then by the pink-colored AVS-2 narrow beam antenna labeled with 4. After missile launch, the wide beam antenna was used for short distances and the narrow beam antenna for longer distances. Once the missile was guided into the beam of the large AVS-1 antenna, this antenna also received the signals from the missile's radio beacon. The monopulse antenna operated in the same way as had been described for the S200 family, see in that video. The signal reflected from the target is divided by the AVS-1 antenna into 3 receiving beams. These are marked with blue, red, green. 2 of which from dual pencil beam, these are marked with red and green. The target tracking system aims for signal minimum for the dual beams, while it aims for signal maximum in the blue pencil beam. Therefore, continuous sweeping was not necessary during target tracking, unlike it was necessary for the Dvina and Volkov systems. The term monopulse refers to the system's theoretical ability to accurately measure all 3 coordinates of the track target, elevation, azimuth, distance with a single pulse emission. In one feature, the KRUG complex was a step back compared to the Dvina and Volkov. The system had a single target channel like its contemporaries, but it had only a single missile channel. Thus the guidance station could engage only one target at a time and only with a single missile. The limitation was due to the missile tracking antennas and the 1-degree pencil beam of the main antenna. Without 2 additional missile tracking antennas, it was not possible to guide additional missiles into the narrow beam of the main antenna. The Dvina and Volkov systems could guide 3 missiles at one target by a single guidance station of a single missile battery. However, a KRUG battalion consisted of 3 missile batteries with 3 guidance stations. Thus, a battalion could still attack one target with 3 missiles, but this required 3 missile guidance radar stations, not 1. On the other hand, the missiles could approach from 3 different directions. Moreover, a KRUG battalion could engage 3 different targets at the same time, which is impossible with a single Dvina or Volkov missile battery. Overall, this meant significantly greater flexibility and firepower, but the level of coordination required was higher, and of course it made a bit more expensive the KRUG, because it needed more guidance stations. Like the Volkov system, the KRUG had a moving target indicator device, MTI, which is called in Russian SDC, for low altitude target tracking. If the target was flying at low altitude, the signals reflected from the ground objects, which are stationary targets, made the detection and tracking difficult. Using the subtraction of successive coherent pulses, the MTI reduced the signal strength of stationary targets. It should be noted that the signal strength of targets with low radial speed also decreased when the MTI was used. The missile of the KRUG only partially resembles those used in earlier Homeland SAM systems. The missile remained two-stage, requiring solid fuel booster rockets to accelerate traveling speed. The booster stages were located on the sides of the missile, similar to the missiles of the S-200 system. The separation and rapid deceleration of the boosters was achieved with asymmetrical aerodynamic cone design. The rocket engine of the traveling stage was still liquid-fueled, but its operating principle was no longer the same as before. For a mobile air defense system, the risk of accidents or damage during movement is significantly higher, so the use of multi-component and highly toxic and volatile fuel was simply not an option. The Berkut, Vina and Volkov SAMs had this kind of fuel. For a mobile army air defense system, the fuel could not be drained from the missiles during each relocation, it had to remain in the missiles. Therefore, the selected fuel was a far more user-friendly and safer kerosene. To use the energy in the fuel with the highest possible power density, the missile was designed with a ramjet engine. This made the single-stage missile design impossible, as the ramjet engine could only be started above the speed of sound. During the service of the KRUG system, 4 missile subtypes were developed and produced: the 3M8 base and the M1, M2 and M3 variants. These were manufactured from 1964, 1967, 1971 and 1974 respectively. The missile length for the two variants was 8.43 meters, while for the shorter-nosed M2 and M3 variants it was reduced to 7.84 meters. More about this change in the extra content. The launch weight of the different missile variants changed minimally. All missile variants were approximately 2,400 kilograms. Interestingly, this was essentially the same as the V755 missile family of the S-75M Volkov had. Compared to the base version, the maximum range of the M1 missile variant increased from 45 km to 50 km. The minimum target altitude decreased from 3000 meters to 250 meters, and the minimum target distance decreased from 11 to 9 km. The first variant was effective against targets performing 4G overload maneuvers, while for the M1 missile the limit increased to 5G. The maximum altitude of the M2 missile variant increased slightly by 1 km to 24.5 km. For the M3 missile variant, the minimum target distance decreased to 7 km, and it was effective against targets performing 6G overload maneuvers. Additionally, the most advanced missile could be launched against receding targets, which feature was not available with the other missiles. The most advanced 3M8 M3 missile variant had a length of 7.84 meters and a total launch weight of 2,453 kilograms. One booster stage weighed 274 kg, of which 173 kg was the rocket fuel. The total weight of the 4 booster rockets was 1096 kg. The booster rockets used the well-proven nitroglycerin powder as a fuel. The burnout time of the booster stage was 4 seconds, during which accelerated the second stage to approximately 400 meters per second, where the ramjet engine became operational. The second, the traveling stage's burnout time was 72 seconds. Top speed was approximately 800 meters per second, which could vary slightly depending on the altitude. Due to the increasing inaccuracy of radio command guidance with distance, the missile had a massive 150 kg warhead similar to the missiles of the Dvina, Volkov and Berkut. 90 kg was the explosive material, the remaining 60 kg consisted 15,000 fragments, each weighing 4 grams. The missiles were carried by the 2P-24 SPU, a tracked self-propelled missile launcher with 3 vehicles per battery, 2 missiles per launcher. A single KRUG battery had the same number of missiles ready to launch as a Dvina or Volkov battery. The launcher had zero-length launch rails. When the 4 booster stages ignited, they practically released the missile in midair. The thrust of the booster stages provided such acceleration that the missile exceeded the speed of sound 300 meters from the launcher. In roughly 4 seconds of operation, it accelerated the missile to Mach 1.8. The launcher was served by a missile transport platoon. This included 6 TZM missile transport loading vehicles and 3 TM, each carrying 1 missile. Guidance of a missile was possible up to a target speed 800 meters per second, a distance of 50 kilometers, and at altitude of 24.5 kilometers. The system's engagement zone with 0 km flyby distance is shown against approaching and receding targets on the right and left sides relative to the vertical axis. In terms of maximum target speed, the system exceeded expectations, while it slightly fell short in maximum target altitude. Considering the operational range of tactical fighter and strike aircraft, this was meaningless. They flew at low to medium altitudes in combat zone and at subsonic speed throughout the entire Cold War period, with a few exceptions. How superior the KRUG was compared to the Volkov? Thanks to the independent missile and target tracking antennas, the KRUG could guide the missile to the target with a greater lead angle. This is theoretically made it capable of countering short-range ballistic missiles, but only within a very narrow range. The KRUG was theoretically effective against short-range tactical ballistic missiles such as the MGM-52 Lance or the French Pluton. Their terminal phase speed remained within the KRUG system's maximum target speed. However, not every operator of the KRUG trained and practiced the crew against ballistic missile targets. The independent tracking antennas provided additional advantages. The Monopulse target tracking antenna did not sweep like those of the Dvina or Volkov systems. Therefore, a separate missile tracking antenna system was needed. The benefit of this was that the angle deception jamming methods that worked against the Dvina and the Volkov in wide-beam mode were ineffective against the KRUG. Against distance denial nose jamming techniques, the 3-point guidance method was fundamental, which the system was capable of even with optical target tracking from the KRUG A variant onwards. The maneuverability of the 3M8 missile of the KRUG always matched or even exceeded the most advanced missile of the S-75M Volkov of the same period. The AVS-1 target tracking antenna formed a narrow 1-degree pencil beam. This provided good protection against the AGM-45 Strike anti-radar missile. Since the emitted beam was very narrow, essentially only the engaged aircraft or another aircraft flying its immediate vicinity would have been able to use the anti-radiation missile against the guidance station of the KRUG. The KRUG had additional operating modes that were entirely unique. The combined features of the SOC radar and the SNR guidance station made it possible these. Let's briefly see how target engagement occurred in case of a maximum range engagement. The guidance station automatically processed the target designation received from the target acquisition radar, and after conducting target search in the area, automatically started to track the target. However, the guidance station did not need to continuously track the target before missile launch with the fire control radar to track the target in angle. If the target was still outside the engagement zone, the guidance station was in PNS, which was the Program Target Tracking mode. In this mode, the SNR did not emit, so it could not be detected. The antenna then followed the calculated trajectory of the target based on the prolongation by the analog computer. The system compared this with the actual trajectory of the target measured by the target acquisition radar. If there was a difference of about 7 to 10 kilometers between the calculated and actual paths, the guidance station briefly illuminated the target to update its actual trajectory and correct the tracking. Compared to the Dvina, Volkov and Neva system, continuous target illumination by the guidance station was not necessary if the target did not perform evasive maneuvers. Thanks to this, the fire control radar did not need to be turned on before missile launch. This reduced the reaction time available to the target. When the calculated missile target interception point was within the missile's maximum range, the guidance station switched to PI, periodical illumination mode. During this mode, the radar transmission by the guidance station was intermittent. The length of the transmission and silent periods was calculated by the analog computer of the guidance station. The fire control radar illuminated the target for the shortest possible time required by the monopulse target tracking, about 1 second. When the guidance station's radar was silent, it was safe from enemy anti-radar missiles. The system essentially automatically applied the short-duration intermittent target illumination used by the Vietnamese Dwina operators, which was a very complicated and very labor-intensive task. See this in the video about the Dwina system. However, since the Dwina did not have monopulse antenna, the illumination periods were longer. The intermittent illumination switched to a maximum pulse density illumination when the missile had been flying for the targets for 10 seconds. What was or what would have been the advantage of this method? The guidance station was relatively protected against even the most advanced AGM-88 HARM missiles of the 80s during certain phases of engagement, as long as the intermittent emission mode lasted. Even if the HARM could attack the KRUG from side lobes, it would have been possible to measure the target's position only very briefly and rarely due to the short and intermittent emissions. Therefore, even the preemptively launched anti-radar missiles likely would have mostly missed their targets. The HARM missile or missiles would have reached the vicinity of the KRUG roughly when the SNR target tracking antenna was still emitting intermittently if the KRUG had launched a missile at all. During Operation Allied Force in 1999, the experience was that the Cold War era AGM-88 HARM, despite remembering the calculated position of the target from the last measurement, could only achieve hit if shutdown of the radar happened at short distance under 10 km. In most cases, even the HARM missile did not hit the target, despite being significantly more advanced than its predecessor, the AGM-45. During the intermittent emission phase in the 60s and 70s, and perhaps even in the 80s, detecting the launch of a KRUG missile with radiation warning system could have been problematic. From this perspective, the system was still unique and perhaps still even modern. If the approaching missile could not be visually detected in time by a pilot, the KRUG would have posed a significant threat to the aircraft. Especially that the ramjet engine with kerosene fuel produced a much less intense smoke trail compared to the Dwina or Volkhov. It made it even harder to spot visually an incoming missile, especially without the aid of a radar warning receiver. The effectiveness of this mode is partially questioned by the need for continuous operation of the target acquisition radar. However, for the SOC to be capable of the described unit operation with the SNR guidance station, its operating wavelength had to be in the decimeter range, not the meter range like the P80 or P12 radars of the Volkhov and Dwina systems. This had serious consequences. The KRUG's target acquisition radar could be attacked by certain versions of the AGM-45. The Shrike was modular and depending on the expected threat, sensors for either centimeter or decimeter radars could be equipped. However, it should be noted that the Shrike's engagement range was far smaller than of the KRUG system. After disabling or destroying the SOC target acquisition radar, target search with the guidance station would have been necessary, which was very slow. Having air situation picture would have not been possible for the KRUG battalion independently without the SOC. In the 80s, the situation changed even more with the appearance of the AGM-88 HARM, which could attack both centimeter and decimeter radars with the same sensor package, utilizing the side lobe signals of the radars. This made the target acquisition radar relatively easy to destroy or disable. The HARM could have easily denied from the KRUG units having a 360-degree target acquisition radar, including the intermittent emission mode. In the 80s, the reality might have been the intermittent use even the SOC target acquisition radar, or the more emphasized use of the target coordinates received through data link from other radars to minimize the use of the SOC. In the absence of the SOC radar, the guidance station would have immediately switched to PI intermittent emission mode in combat operation. What was a serious advantage before the HARM era, maybe it was a disadvantage in the HARM era. The KRUG could guide missiles with half-lead method, but based on the experiences from Vietnam, the 3-pot guidance method was the standard except for extremely high altitude and high speed targets. Against noise jamming targets, knowing the distance was not necessary, and the monopulse antenna could track the noise jamming target. The noise jamming just made the target tracking easier. For tactical fighters and strike aircraft, the rules of engagement dictated the use of the 3-point method. After missile launch, the accelerating missile entered the waiting gate zone. Here, with the help of the missile's onboard beacon, automatic tracking of the missile began with the AVS-2 wide beam antenna. Based on the measured data, the missile tracking antenna tower was turned so that the missile was within the receiving zone of the narrow beam antenna. The missile tracking channel then switched to the narrow beam antenna, and based on the more accurate data, the analog computer determined the further counter commands. When the missile entered the 1-degree pencil beam of the AVS-1 monopulse target tracking antenna, it received both the missile's transpondance signal and the target signal. With 3-point guidance, this happened almost from the beginning of the guidance. In the presented video clip, we can see the KRUG system during relocation, the deployment, the checks, target search and data transfer from target acquisition radar to the guidance station, then finally missile launch and guidance. Now we can understand how much more complex the KRUG was compared to the Volkhov, which also influenced its export. The Soviet Union introduced its first version in 1964. The modernization programs of the KRUG lasted until the mid-70s. The KRUG remained in production until the end of 1982. Continuous upgrades led to the appearance of the KRUG A, KRUG M, and finally the KRUG M1 variants. Thanks to its capabilities, the KRUG system was never exported outside the Warsaw Pact member countries, therefore it never participated in combat. This is likely why the system and its capabilities are less known and published in the West. In my opinion, this also partially explains the confusion between the P-14 complex and the SOC radar, as it's easy to mix them up due to the lack of information. Among the Warsaw Pact member states, all except Romania acquired the KRUG system. Czechoslovakia, Poland and Bulgaria each acquired one brigade. Hungary was the last to deploy the KRUG system, along with Bulgaria in 1981. Interestingly, two countries, Hungary and the German Democratic Republic, or more commonly known as Germany, had only KRUG regiment instead of a brigade. The KRUG regiment had only 2 battalions instead of 3, so it had only 6 target channels instead of 9. In Hungary, a total of 2 Soviet KRUG brigades and 1 Hungarian KRUG regiment were deployed in Transdanubia. The Hungarian People's Army 7th Air Defense Missile Regiment had 2 battalions in Keszthely, while the Soviet Southern Army Group had 2 full brigades stationed in Dunaföldvár, Igal, Mol, Fertőd, Pápa and Sármellék locations. After the end of the Cold War, most of the former Warsaw Pact member countries retired the KRUG system relatively quickly. Hungary retired in autumn of 2000 and the last operator, Poland, in 2011. Among the successor states of the Soviet Union, several kept this system in operation in the 1990s, but by now they are likely only in service on paper or not at all. One of the grave diggers of the KRUG was the development of the digital telecommunications. The operating frequency of the P-14 complex target acquisition radar and the 1S-12 SOC radar at 2100 MHz were the same what the 3G cell phone towers used. The capitalism won over the aging SAM system. If you like the video, you can share, like, subscribe or ring the bell and follow the channel. You can support it via Patreon or YouTube channel membership for exchange for early access, voting on planned topics, extra content and updates about the projects. So far 15 extra content had been released, their description are the link under the video.